Hi, hello students. Welcome to BYJU'S Exam Prep. This is Anil Prasad Sir. In today's class, we are going to, discuss the remaining things in computer organization and architecture. In yesterday's class, we discussed about a few things. That is the CPU design and all the entities within the CPU. Right? So we solved a few questions in CPU design. In today's class, we are going to discuss and solve rest of all the other topics question. So we will try to solve as many questions as possible. So stay tuned and share this session as much as possible so that the other students will also be able to capitalize on this session, and so that they will give the BARC HAL with an utmost confidence in terms of computer architecture and organization. So let us start without having any delay at all. So before I proceed into the things, let me once again remind you that there is a session on 13th March, which is on strategy to conquer GATE 2023. You will be able to get every idea what are the strategies and what are the steps to follow for the GATE 2023. So don't miss this session and share this session to as many people as possible so that they will follow, and all the GATE aspirants for GATE 2023, they will be able to understand what are the things and necessary steps and what are the prerequisites to crack the GATE exam, which is a 2023. Yeah, let us start this. Yeah, yesterday we discussed about the CPU design. Today's class, first we will discuss about the memory. In the memory, we will discuss about a few things, that is the cache memory and the other detailed logic of the RAM and ROM chip constructions. So we will take the questions one by one and we will try to solve this. Okay, so to start with, this is the question. Consider the two-level cache hierarchy L1 and L2 caches. An application incurs 1.4 memory access per instruction on an average. For this application, the miss rate of L1 cache is 0.1 and the L2 cache is experiencing on an average 0.7 misses per 1000 instruction. The miss rate of L2 expressed correct to two decimal places is what? This is the question. Could you please answer me? Either is option A, option B, option C, option D. Yeah, hi Anu, could you please tell me what is the answer for this? Consider two-level cache hierarchy. The system is following two-level cache. We know that we can have any number of cache levels, but most of the times in order to have a feasible construction, we need to have a feasible design. Most of the times, most of the designers, when it comes to the simple CPUs, they will go for two-level caches in which L1 and L2 will be the integral part of the memory hierarchy. So an application incurs 1.4 memory accesses per instruction. When instruction gets executed, it requires 1.4 memory accesses. For this application, the miss rate of the L1 cache is 0.1 and the L2 cache experiences on an average 7 misses per 1000 instructions. So what will be the miss rate? Option is 0.07. I don't think so. I don't think so. I will explain you in the very simplest possible way. Just try to understand. Okay, here it is given that 1000 instructions, right? Let me write. This is the an application, let us say, which has 1000 instructions in it. Okay, these 1000 instructions, when they get executed, first of all, you know that in L1 cache itself, this is the L1 cache. From L1 cache itself, 90% of the instructions will be found, because it is very clearly given that the miss rate of L1 cache is 0.1. That is, hit rate of the L1 cache is 0.9. When it comes to the percentage, it will be 90%. 90% of the instructions will be found just in the L1 cache, right? So out of 1000 instructions, L1 cache, from L1 cache, we will be able to find out 900 instructions. We will be able to fetch 900 instructions right from L1 cache itself, right? So for the remaining 10%, we will access L2 cache. That is, how many instructions? For how many instructions? Out of 1000 instructions, you just got 900 instructions from L1. Remaining 10%, that is, only for 100 instructions, you need to go to L2 cache. This is the scenario you need to understand. If you think sensibly, you will get this picture in your mind. So only for the 100 instructions we need to access L2 cache. Here you know that 100 instructions meaning 140 memory access, right? 100 instructions meaning 140 memory accesses. So what is given here? The L2 cache experiences on an average 7 misses per 1000 instructions. So out of 1000 you just got 900 instructions in L1 cache itself. Only for 100 instructions you are going to L2 cache. So out of 100, when the memory access are equal to 140, you are just experiencing 7 misses, right? So 7 in 140 is 0.5%. When it comes to the rate, it is 0.05. I hope I made it clear. So simple thing is, out of 1000 instructions, 900 instructions we are able to find in L1 itself. Only for 100 instructions we are just going to L2. For all these 100 instructions, we know that the total number of memory access that are required is equal to 140. Out of 140 memory access, we are experiencing 7 misses. 7 in 140 is 0.5. When it comes to the rate, 0.05. Did I make it myself clear? Yes or no? Any doubts in this? Shall we go to the next question? Hi, Anu. Can I go to the next question? Yeah, fine. Let us go to the next question here. Yeah. In a two-level cache system, the access times of L1 and L2 are 1 and 8 clock cycles, respectively. The miss penalty from the L2 cache to the main memory is 18 clock cycles. The miss rate of the L1 cache is twice than that of L2. The average memory access time of this cache system is 2 cycles. The miss rate of L1 and L2 respectively are option A, option B, option C, option D. May I know what is the answer for this? For this, see, you will be able to solve this by applying the same logic, but I'll give you a shortcut in order to solve this. You know that average memory access time will be calculated as, do we have a slide for this? Yeah, I don't have a illustrative slide, but I will explain here itself. Average memory access time will be calculated as, in general scenario, average memory access time is equal to H1 T1, where H1 is the hit ratio of the first level cache, T1 is the hit latency of first level cache, that is the access time of first level cache, plus 1 minus H1. Why we need to go to the second level cache? During a miss in first level cache, right? So this is miss rate of the first level cache into H2, hit rate of the second level cache into the time which we have spent at first level cache plus the time which we require to access the second level cache. So H1 T1 plus 1 minus H1. Why we are going to second level cache? During a miss only we will be able to go to second level cache. That is 1 minus H1, which is the miss rate of the first level cache, into H2, hit rate of the second level cache, into T1 plus T2. The time that we spent and wasted in the first level cache and the time that we are going to spend in order to access the second level cache, plus why we go to the main memory? During a miss in first level cache, the miss rate of the first level cache, and also during a miss in the second level cache. In the first two caches, if we experience a miss, then only we go to the main memory. So that we need to add first level cache miss time, first level cache miss rate, second level cache miss rate into the time which we wasted at the first level cache, the time which we wasted at the second level cache, plus the time that we are going to spend in accessing the main memory, T1 plus T2 plus T3. It is the average main memory access time, right? But sometimes the designers of the question won't provide you with the hit ratio or hit rate. If the hit rate is not given, what we must do? For that, let me take you to the illustrative slide. Yeah, here I will give you one shortcut rule or shortcut formula when we are not provided with the hit rate. Okay, if the hit rate is not provided, let us understand. average memory access time will be equal to okay, T1 when we are not provided with, this is the shortcut formula, T1 plus miss rate of L1 into T2 plus miss rate of L1 into, I will write it here, miss rate of L2 into T2 plus T3. When we are not provided with a hit rate, you can use this formula. From where I got this formula? Did I, am I incorporating my own formula? Did I design my own formula? No, in fact, I'm not designing any formula. Rather than I'm using the same formula. If you actually can have a look at this formula, is a simplified formula of the actual average memory access time, which we have discussed just a few seconds ago. This is a simplified formula, simple. As we are not provided with the hit rate, we just simplified the formula according to the question, because there we are provided with some miss rate, that too by a ratio, but that too by a relation. Let me explain. No, Arnab, let us understand. This is a simplified formula. In the simplified formula, in the, here you just will get T2. Okay, here you will get T2 plus T3. If it is not simplified, it will be T1 plus T2, but here it will be T1 plus T2 plus T3. It is a simplified formula that we are going to use whenever we do not have the hit ratio with us. Yes or no? Got my point? Got my point or not? So now calculating this will be very simple. Average memory access time is given as 2. Okay, and now what is T1? Let me go and check. What is T1? T1 is access time. T1 is 1, right? T1 is 1 plus what is miss rate of L1? I think miss rate of L1 and L2 are given with a relationship. The miss rate of L1 cache is twice than that of L2. Very good. So what we'll do is L1 I'll miss rate will be 2x. Okay, L2 miss rate will be x, L1 miss rate will be 2x. Yes or no? Because it is double. I will simply think that L1 miss rate will be equal to 2x and L2 miss rate will be x. Okay, what is T2? T2 is 8 clock cycles as it is given in the question, plus what is miss rate of L1? Miss rate of L1 is 2x plus miss rate of L2 is x. T2 plus T3. What is T2 plus T3? T2 plus T3 has also been given in the question. That T2 plus T3 is also given in the question. That where it is? Yeah, the miss penalty from the L2 cache to the main memory. So here if you say miss penalty from the L2 cache to the main memory, here he included only 2 terms, that is L2 plus main memory. Miss penalty will include the time which we have spent and wasted at the L2 cache and the time that we are going to spend also in the main memory. So 18 clock cycles is T2 plus T3. Okay, T2 plus T3 is equal to 18 clock cycles. So you just simply plot this 18 clock cycles. Okay, so it will be equal to 1 plus 8 into 2x is equal to 16x plus 36x square is equal to 2. So I can say that 36x square plus 16x minus 1. Yeah, minus 1 is equal to 0. Okay, if you factorize, you will get x as 0.056. If you factorize, x is equal to 0.056 and 2x is equal to 0.111. This is the actual option and this is the answer. Did you people get this or not? Can you go to the next question? Can you go to the next question? So option A is correct because we are asked clearly understand L1 and L2 misrates of L1 will be equal to L1 misrate will be equal to 0.11. So L1 misrate is 2x, right? Okay, this 2x is L1 and this x is L2. Yes, we solve it correct. L1 misrate is 2x, which is 0.111. L2 misrate is equal to 0.056. Option A is correct. Can you go to the next question? Yeah. Consider a two-way set associative cache with 256 blocks and uses LRU replacement. Initially, the cache is empty. Conflict misses are those misses which occur due to the contention of the multiple blocks for the same cache set. Compulsory misses occur due to the first time access to the block. The following sequence of the access to the memory blocks are this one. So it is repeated for 10 times and the number of conflict misses experienced by the cache is what? This is the question and now we need to answer this. So first of all, in order to solve this, we need to have an idea. What is a miss? You know that what is a miss? In cache, if we are searching for a word and we are failed, that is just nothing but a miss. A miss is a miss anyhow. But by the way we experience a miss, we can classify the misses in three categories. Those are, the first one is compulsory miss. Second one is conflict miss. And the third one is capacity miss. What is the compulsory miss? If you are searching for any word for the first time within the cache should produce a miss, which is called a compulsory miss. Next one is a conflict miss. What is a conflict miss? See, when a main memory block is mapping to one specific block of the cache memory, in addition to one more block, we are going to experience a conflict miss. Let us say a memory block X has to be transferred to cache memory. Okay, this X block will have to be mapped to a certain block within the cache memory. But already there, the cache memory has one more block because this X and the already available block Y are actually mapping to the same set because of the mapping technique. Okay, so X now is going to experience a conflict miss because X is going to replace one more block which is already there in the cache memory due to the conflict of the indexes. So this is called a conflict miss. The third one is a capacity miss. What is a capacity miss? Capacity miss is very simple. When you switch on the computer system, the cache will be completely free. Okay. So but right after you start executing the programs, sooner or later, cache will be completely full. Okay, because cache is very small. Sooner or later, cache will be having some or the other data. Finally, the cache will be completely full. Right after the cache is completely full, any more misses will be falling under capacity misses because the cache capacity is finished. Right after which, if you experience anything, any miss, that will come under, that will be called as a capacity miss. Now here we are asked about the conflict misses. How many conflict misses that we are going to experience in this case? Okay, so let us understand. So I know that most of the people, they solved it very clearly. For that, I will give you a proper way to solve this. Understand carefully. Okay, even see, if you have everything in your mind, we don't even need to draw any block diagram. Straight away we can say that we can, looking at the string itself, we will be able to understand what will be the total number of conflict misses. I will explain you that shortcut only right after I explain you by using a block diagram. Total number of blocks will be equal to 256, right? Okay, 256 blocks. And 256 block, absolutely, 8 into 9 is equal to 76. Perfect. 256 divided by 2 is equal to 128, right? So there are a total of 128 blocks. There are a total of 128 blocks. Okay. 0, 1, this is 0 block, this is the 1th block, and so on. We don't need to consider any other thing because all the block numbers of the main memory are just getting mapped to either 0 or 1. What is the mapping rule? Mapping rule is the referenced block number mod total number of sets in the cache memory. So 0 mod 128 is equal to 0. Of course, 128 mod 128 is equal to 0. Till here, all the block numbers are getting mapped to 0. From 1 to 129, all the blocks are getting mapped to the first block. So we don't need to, draw the remaining blocks here. We just need to take care of the, we just need to draw only 0 and 1 here. So each and every set is having 2 blocks. So first one is 0. What is 0? 0 is the compulsory miss. 1 is the compulsory miss, right? Right after which 256. 256 is going to replace 0, right? Even this also is a compulsory miss. 0, 128 and 256 are compulsory misses. And 128 right now, 120, 0, sorry, not this one. This is 128. Sorry, 0, 128, 256. Right after which 128 is a hit. Right after which 0. Now 0 is a miss. Okay, 0 is a conflict miss. So 0 will be here. Okay, 128 is a hit. Then 256 is going to replace 0. Okay, now how many conflict misses for this? 2. Initially I got 2 here. Same scenario will also happen here. 1 and 129 will be here, which are compulsory misses. After which 257 is going to replace 1 here. Okay, right after which 129, every time 129 will be hit, but 1 and 257 are misses. Initially, for the first time, there will be 4 conflict misses. I will write it here. This one will be replaced by 257. Okay, right after 257, 129 is a miss. After which 257 will be replaced by 1. I am writing here. Okay, this is a conflict miss. Again 129 is a hit and 257 is a miss. So 1 will be replaced by 257. Got me? Initially, in the first iteration, I just got 4 conflict misses. Right from the second iteration, everything is a conflict miss, right? So here 128, 128, 128, 128 are hits. Remaining all 0 is a miss and 256 is a miss. 0 is a miss, 256 is a miss. Okay, so these are 4. And similarly, here 1 is a miss, 257 is a miss, 1 is a miss, 257 is a miss. So a total of 9 into 8. Okay, 9 into 8 will be equal to 72 plus the first 4 will be equal to 76. We experience a total of 76 conflict misses. Did I make myself clear, or you want me to explain anything more here? Are we done? Can I go to the next question? Can you go to the next question? Arnab? Anu? Yeah. Next thing is, in designing computer's cache system, the cache block or a size is an important parameter. Which one of the following statements is correct in this context? A smaller block size implies better spatial locality. A smaller block size implies smaller cache stack, hence lower cache stack overhead. A smaller block size implies larger cache stack and hence lower cache hit time. A smaller block size incurs a lower cache miss penalty. Among which is the correct option? Which is the correct option? Anu, did you understand the previous question? Participate so that the knowledge transfer will happen in a proper way. Anu, did you understand the previous question? Where is Bhumi here? Yeah. Any ideas? How to solve this? Listen, I will tell you. Okay, forget about this. C is not a correct option. But let me give you a complete idea. For this, let me take a counter example. The counter example is, let us say, my main memory. Tell me, give me a main memory size. Can I take 4 MB? 4G. I will take 4 GB main memory. Okay, and the cache memory is 32 KB. Got me? Main memory is equal to 4 GB and cache memory is equal to 32 KB. and the block size is equal to 32 words. 32 words or bytes, whatever you call. Okay, this is the thing. Stay focused here. Now 4 GB. Let us divide index plus tag. Initially, you know that. The total main memories, the total address bits must be divided into index plus tag. What is index? Index is total number of bits that are needed to represent a cache memory. So for this 32 KB, we do require 15 digits. In order to represent the cache memory, I do require 15 digits. So index will be equal to 15 digits, right? The remaining bits will be equal to tag, right? Yes or no? Index will be 15 and the tag will be 17. Here, index will be further subdivided into two more fields. That is the word field and the number of blocks. What is the word field? Word field is the block size. Block size will give you the word field. 32 words. A block is equal to 32 words. So word field will be equal to 5 digit because 32 words require 5 digit. I will write it here. Number of words per block. Number of words per block equal to 32, which require 5 digits. So least significant digits, which is the word field, will be equal to 5. And then now here, 15 minus 5 is equal to 10. So in my system, I do have a total of 2 power 10 blocks. 2 power 10 blocks and 2 power 5 words. Okay, so in my cache memory, a total of 2 power 10 blocks with each block of 2 power 5 words are available right now. Let us understand carefully. See, here he is talking about updating the number of words. Okay, block size, a smaller block size, meaning he just want to reduce the block size. If the block size is reduced, let us say the block size has been reduced from 32 words to just 16 words. If the block size is reduced, here the number of bits that are needed to accommodate for the word field will be equal to 4 and number of blocks will get increased. If the block size gets reduced or affected, number of blocks will get affected, but not the tag field, right? The effect of the word field is going to affect the number of blocks. This middle field will get affected. Tag will not get affected. Did I make myself clear, or you want me to explain even more further? Yes or no? Got my point? So there is nothing. See, straight away I can rule this B and C, because if you affect the block size, number of words of the block will get affected, so the number of blocks of the cache memory will get affected. So the tag will nowhere be considered to be affected at all. So a smaller block size implies smaller cache tag, hence lower cache overhead. This is wrong. A smaller block size implies the larger cache tag and lower cache hit time. No, this is also, he's talking about affecting the block size and affecting the tag. Tag will not get affected due to the updation in the block size. So B and C will be completely ruled out. Okay, a smaller block size implies better spatial locality. Now understand what is this? Is it making any sense? If you want to have a better spatial locality, the block size should get increased, right? Tell me, what is the locality of reference? There are two locality of references: temporal locality, spatial locality. What temporal locality states? Temporal locality states that if you access a word right now, that word will be accessed in the near future. For that purpose, you need to bring that word from the main memory and to place it in the cache memory. It is talking about only one word. But when you talk about a spatial locality, let us say I'm accessing 23rd instruction in the main memory. Temporal locality states that 23rd instruction you are accessing right now. In the near future also, there is a greater chance for the 23rd instruction to be accessed. Please bring the 23rd instruction and place it into the cache memory. So tomorrow when the 23rd instruction is being accessed, you don't need to go to the main memory. This is what temporal locality states. Spatial locality just enhances the temporal locality. And he will ask you, when I am bringing the 23rd instruction and placing into the cache memory, spatial locality states that you don't bring just 23rd instruction. if you execute 23rd instruction right now, tomorrow you just need to execute 24th instruction, after which you need to execute 25th instruction, 26th instruction. You may also execute 19, 20, 21 or even 15, 16, 17 if your current instruction is in a loop. So what you do is, in addition to the current accessed element, the elements that are maintaining the closer proximity, please bring them into the main, please bring them from main memory to the cache memory. So spatial locality will always ask you to bring a block of words from main memory to the cache memory in which the currently accessed element is a part. Okay, so simple thing is, if you do have a bigger block size, more spatial locality, smaller block size, less spatial locality, right? So D is right. Obviously, smaller block C. Listen, that also we need to legally prove. Sometimes D can also be wrong, but we need to legitimately come to the conclusion that the D is correct. Smaller block size incurs lower cache penalty. If the block size is smaller, number of blocks will get increased, right? Yes or no? I do have total 10 words, okay, and the block size is equal to 2 words. So I can have 5 blocks, okay, and the block size is just 1 word. I can have 10 blocks. So when the number of blocks gets increased, obviously our chance of getting a hit every time also gets increased, right? Yes or no? When the number of blocks are more, am I having a greater chance of hit or lower chance of hit? Of course, I do have many blocks. If one block, if not one block, there might be another chance of having a hit in another block. Got my point? So D is correct. Smaller block size implies better spatial locality, which is actually contradicting. Smaller block size implies smaller spatial locality, the worst spatial locality. So smaller block size doesn't affect the time. So B and C will get ruled out. D, smaller block size. When the small block size is smaller, number of blocks will get increased. So obviously the chance of having a hit every time will get increased. So option D would be the right option. Okay. Normally user programs are prevented from handling IO directly by IO instructions in them. But the CPUs having explicit IO instructions, such IO instruction is ensured by having the IO instructions privileged. In the CPU with the memory mapped IO, there is no explicit IO instruction. Which one of the following is true for a CPU with the memory mapped IO? First of all, my question is, do you got any idea what is this memory mapped IO, or the other techniques of mapping? There are actually three ways. We can have the bus system. Of course, the bus system is not mentioned here, but according to the way we talk about the bus system, which is going to carry the information both main memory as well as the IO devices, we can have 3 different kinds of bus systems. The first one is distinct IO. Okay. Second one is isolated IO. Stay focused and just listen and just get it important in your brain. Third one is memory mapped IO. These are the 3 ways I can have my bus system configured in my system. What is a distinct IO? You know that bus system has 3 entities. The first one is the address bus, second one is the data bus, and the third one is the control bus. Okay, in the distinct IO, we use a separate processor. There is the IO processor. So I need to communicate from CPU. From the CPU, I need to communicate 2 things. One is main memory, one more is IO devices. So I will use 2 separate bus systems. One is to the main memory and one more is to the IO devices. So CPU has no problems whatsoever. So it has 2 separate bus systems. So no data transfer will actually have to wait for the other transfer to happen. So in this case, the complexity is I need to have one more CPU which actually takes a load of IO transfers. Okay, you can use Intel 8089 or IBM channel, whatever. You just can use any of the IO processors. But if you talk about distinct IO, which talks about 2 separate bus systems, you need to have 2 separate processors. One is for regular processor, let's just like 8086 or Intel i3 or i7. But one more will be exclusively for IO transfers. It could be Intel 8089 or IBM 370 channel. So distinct IO, but it is costly. So we can have only 2 options: isolated IO and a memory mapped IO. What is the job in our hands right now? Without having any hassle, we should be able to communicate with both IO devices as well as the main memory. How we can do it, how we can achieve it by using a single bus system. In the isolated IO, there will be one address bus, there will be one data bus, but there will be two control buses. Let us say control bus 1 will be for the IO devices, control bus 2 for the main memory. Let us say if there is an address present in the address bus and the data present, data is anything, my name Anil. This Anil has to be transferred to 250th location. But which 250th location? This 250th location is available in main memory as also available in the IO device registers. There are two separate addresses. So to which device actually I am transferring? I just need to look at the control one. If the control one is active, then that means that this transfer will be pertaining to the IO devices. Otherwise, the control line 2 is active, then this transfer would be pertaining to main memory. Got me? And now, the third one is memory mapped IO. In the memory mapped IO, there won't be even no control, second control signal. Only one control line will take care of the total transfers. Address bus, data bus, and a control bus. What is the address bus? Of course, address bus will talk about the address. Data bus will talk about the data that is needed to be transferred. But how it has to happen? Simple thing is, I will give you one wonderful example here. Let us say I do have my main memory. My main memory is equal to 1000. And even in the IO devices, I do have few interface registers, altogether 250. Okay. Now, in the isolated IO, the address range of the main memory is 0 to 999. The address range of the IO device is 0 to 249, right? So let us say if there is an address 25, 25 is falling under both address ranges, main memory as well as the IO devices. So actually, the transfer has to pertain to which device, main memory or IO device. So you don't need to worry, just you need to have a look at the control signals. If the control signal 1 is active, this transfer is to main memory, the IO device. If the control signal 2 is active, then the main memory transfer is initiated. But now, during the memory mapped IO transfer, in the memory mapped IO bus system, what will happen is, computer system calculates the total address range. That is, it will club main memory address range plus IO address range together. So the total address range of the computer system is 1250. Okay. And it treats that this total address space does belong to only main memory. And the computer system don't feel that there is a IO existence. Computer system doesn't treat IO devices separate. IO device address space also will be clubbed with the main memory address space. Our CPU treats the total address space as a single address space. It's a memory address space. Got me? So in this case, what will happen is, of course, we don't have any, ambiguity here. 0 to 900, 0 to 999, it will be pertaining to memory transfer, and 1000 to 1250, it will be pertaining to IO transfer. But only the problem is here, there won't be any specific IO instructions. If there are no IO instruction, how the protection is possible? If there is an IO instruction is a protected instruction. IO instruction is a privileged instruction, because when the IO instruction is executed, you are going to access your IO devices. None of the IO devices can be accessed directly by the user. When an IO instruction is executed, the IO instruction will be executed by the CPU on behalf of the user to get the IO devices completely protected. But here, there are no IO instruction. Any instructions which accesses the main memory can also access the IO device. So there is no distinction between memory instructions and the IO instructions. So how the protection is possible? The protection is possible by the operating system itself. IO protection is ensured by the operating system routines. So operating system should take a necessary care that whenever an IO device is accessed, that has to be protected in such a way that the user program, the mistakes should not affect the IO device. Did I make it myself clear? Yes or no? Any doubts here? Yeah. Let me go to the next question. I hope you got it, and just keep the notes of all these things right now. Yeah, it's a good question. A graphic card has an onboard memory of 1 MB. Which of the following modes can the card not support? 1600 400 resolution with a 256 colors of on a 17-inch monitor, and 16 400 resolution on a 16 million color on a 14-inch monitor, 800 400 resolution with a 16 million colors on a 17-inch monitor, 800 resolution with a 256 colors on a 14-inch monitor. Which is the correct one? You don't need to go to computer architecture at all. We just need to be sensible in solving this question. You will be able to get this option. It's simple. What is this? Meaning what? I didn't get you. I didn't get you. Yeah. Fine. You just if you can enhance your question, I will be able to. It's not a multimedia question. Of course, it belongs to the CPU architecture itself. Okay, because it is talking about memory. Okay, in the main memory, see, in the main memory, we'll have two other memories also. One is graphic card memory. One more is control memory. Okay, these two questions can also belong to main memory. What is the graphic card memory? There will be an exclusive memory card will be allotted for supporting the graphics. What is the control memory? If you follow, rather, if you design your control unit in terms of a micro-programmed control unit, you will have one more memory unit that is connected to the system, which is called a control memory. Any memory will be a part of the main memory. The computer system treats every memory as a part of a single memory unit. So this belongs to main memory itself. So how to solve this question? So it is simple, as I told you. You don't need to brush any concepts. It's a simple common sense question. The graphic card has an onboard memory of 1 MB, which has the following modes can the card not support. Which of these things the card wouldn't support? Okay, so here the available available graphic memory is 1 MB. Everything must be, any resolution must be in between more or less 1 MB, not more or less, should be well under 1 MB. If anything crosses 1 MB, that doesn't support. Simple. Here, simple, monitor size will not have any effect on this, because monitor size talk about pixels, pixel density. We don't talk about the monitor. Monitor doesn't come into the aspects of the main memory. So monitor you don't need to take care of. Only the thing is you need to calculate what is the memory required for each case. Here 1600 into 400 resolution for 256 colors. For 256 colors, I do require 1 byte. Am I clear? 1 byte meaning 8 bits. In order to represent all the 256 colors in a color spectrum, I do require 1 byte. Am I clear? Okay. And I do have 1 byte. For this 1600 into 400, what is the total? 16 into 4 is equal to 640. Yes. 1600 into 400 is equal to 640K. Okay. These are the 640K combinations into 1 byte. Okay, so 640 KB is well less than 1 MB. So this will support. Second one is 1600 into 400 resolution with a 16 million color on a 14-inch monitor. What is 16 into 4? Again the same thing. 640K will remain the same, but 16 million is 2 power 24. 2 power 24 meaning I do require 3 bytes, right? Okay. Here, the size, the combinations will be to 640K. 640K, at each combination, I do require 3 bytes. Okay. So, 3 bytes into 640K will cross more. 640, it will cross well over 1 MB. So, it doesn't support. Third one is 800 into 400 resolution with a 16 million color and a 17-inch monitor. I hope this satisfies. 4 into 8 is equal to 32K, 320K. Okay, 320K and a 16 million color. 16 million color, 320K into 3 bytes. Right? 320 into 3 bytes will be 960 KB. 960 KB is less than 1 MB. So this also supports. And 800 into 800 resolution with a 256 colors. If you translate it to, you will simply get 640K. This 640 KB will support. 800 into 400 will support. First one will also support. Only B, the option B, 1600 into 400 resolution with a 16 million color on a 14-inch monitor doesn't support because it is crossing the capacity of the graphic card that is attached to the system. Okay. Okay, but no, it is not. Yeah. Next question is, yeah, a CPU has a cache size with a block has a cache with a block size of 64 bytes. Stay focused. Stay focused. The main memory has k banks, each bank being c bytes wide. Consecutive c byte chunks are mapped on consecutive banks with a wraparound. All the k banks can be accessed in parallel, but two accesses to the same bank must be serialized. Fine. A cache block access may involve multiple iterations of parallel bank access depending on the amount of the data obtained by accessing all the k banks in parallel. Fine. Each iteration requires decoding the back numbers to be accessed in the parallel, and this takes k by 2 nanoseconds. The latency of the bank access is 80 nanoseconds. Fine. Got it completely. Now, let us have a look at the details that are provided within the question. Question looks lengthy, but if you decode in a proper way, the question looks very simple. Looks lengthy, but it's a simple question. First, you go and understand what is the size of the main memory. I will let it show. First, we will go to main memory. Main memory has k banks. Okay. Main memory has k banks. Okay. What is k? K is equal to 24. There are total 24 locations in the main memory, and each bank is equal to c bytes. So each bank is equal to c bytes. What is c here? 2 bytes, right? So the total main memory is equal to 48 bytes. The total main memory is 48. There are 24 locations, 24 words. Each word is of 2 bytes. Simple. In some other words he has given, in some tricky manner he has given, but when we translate it to the appropriate, the words, we got that 48 bytes. The total size of the main memory is equal to 48 bytes. Fine. Now let us go to what is the size of the cache memory. Cache memory size is equal to 64 bytes. This is purely hypothetical. There is no ever way that a cache size can exceed main memory size. But here, the total main memory is not even equal to one block in the cache, right? One block in the cache itself is 64 bytes. Okay, 64 bytes. Now here, what he said is, main memory can be completely accessed in parallel because all the banks can be accessed in parallel. There are a total of 24 locations in the main memory. All the 24 locations can be accessed in parallel. But if you want to access one bank twice, you just need to serialize this. Let us say you want to first access the first bank twice. So obviously you need to serialize. Right after the first access, you need to go for the second access. Right? So this is also not a big thing. So let us have a look at. Now the thing is, when there is a missing cache, we need to transfer from the main memory. But the cache block size is 64 bytes. Main memory has just 48 bytes. So we do require two transfers. Once we need to access the main memory to transfer 48 bytes to the cache memory. 48 bytes is not sufficient because during every transfer the complete block has to be full, right? So for that we need to access the main memory for twice. So how it would happen? That is, the latency of one bank access is equal to 80 nanoseconds. So one access is equal to 80 nanoseconds plus somewhere k by 2 nanoseconds latency of one bank access is, wait. Data obtained by accessing k banks in parallel. Each iteration requires decoding the bank numbers. Decoding the bank numbers is k by 2. So every access will require 80 nanoseconds plus decoding the bank numbers will take k by 2 nanoseconds, which is equal to 80 plus k by 2 is 12. So one access will be equal to 92 nanoseconds. Why I did specify only one access here? Although he specified one bank will be accessed in 80 nanoseconds, it is clearly given that all the banks can be accessed in parallel. So, for all the banks, as they can be accessed in parallel, for accessing every bank, total main memory, I do require 80 nanoseconds. In addition to which, all the banks must be decoded, right? Which takes k by 2 nanoseconds. So, 92 nanoseconds I do require in order to transfer just 48 words into the cache memory. But I need to access the main memory for twice. I don't have no other option because cache memory has, one block is equal to 64 words. So only 48 words will be filled in one block. So remaining words in order to transfer, I will need to access the main memory for one more time. That is 92. 92 plus 92 is equal to 184. So 184 nanoseconds is the correct option. Got me? Yes or no? Can we go to the next question? Consider a four-way associative cache with a total 16 cache blocks. The main memory consists of 256 blocks and the request for memory blocks is in the following order: 0, 255, 4, 3, 8, 133, 159, 216, 129, 63, 8, 48, 32, 73, 92, 155. Should I repeat? Okay, fine. Yeah, listen. Anu, answer me a question. Arnab, I do have a question here. What is the size of, type it here, I will wait. I will make you people answering this. What is the size of the cache memory? Type, make it fast. Arnab, Anu or Pooja or whoever you are, just answer to my question. What is the size of the cache memory? 64 bytes, right? What is the size of the main memory? What is the size of main memory? What is the size of main memory? 48 bytes, right? Yeah. In one access, you will be just able to send only 48 words. Okay, one access will transfer just 48 words, but not 64. Is the 48 words sufficient to fill one cache memory block? Got it? So, only for one transfer, you will require 92 nanoseconds, but we need to access main memory twice in order to make a complete block accommodated within the block of the cache memory. I hope you got it. Anu, got me? Yeah. Two times. Twice we need to transfer. Anu, did you understand this? Yeah. I'm just going to the next question. You there, Anu? Fine. Consider a four-way set associative cache with a total of 16 cache blocks. The main memory consists of 256 blocks and the request for the memory blocks is in the following order. Which one of the following memory block will not be in the cache if the LRU replacement policy is used? Okay. So let us have a look at this. Total 16 blocks. 16 blocks and four-way set associative. That means that there are just 4 sets. There are just 4 sets. Each set has 4 blocks. Okay. First set, second set, third set, and fourth set. Now, what is the mapping technique? The referenced block of the main memory mod total sets in the cache memory. Total sets will be equal to 4, and the reference block mod total sets will give you the thing. So, where 0 is getting mapped, 0 will get mapped here. 255, I think 255 will get mapped in 3. 0, 1, sorry, 0, 1, 2, 3. 0, 1, 2, 3. 255 will get mapped to 3. Yes, 3. Okay. 1 will get mapped here. 4 will get mapped here. 3 will get mapped here. 8 will get mapped here. 133. 133, I guess it is 1. Will be mapped to 1. 159. 159. Yes, it is 3. 159 will be mapped to 3. Is it making any sense or not? Because I am using the mod rule here. What is the mod rule? Main memory reference block. 0 mod. What is the total number of sets here? 0 mod 4 is equal to 0. Right? 255 mod 4 is equal to 3. 1 mod 4 is equal to 1. 4 mod 4 is equal to 0. 3 mod 4 is equal to 3. 133 mod 4 is equal to 1. 159 mod 4 is equal to 3. 216 mod 4 is equal to 0. Okay. and 129 mod 4 is equal to 1, I guess. Am I clear? Yes. 128, 129. Sorry. 63 mod 4 is equal to 3. Hold on. 63. Where am I? Did I miss anything? 156. 3 is here. 129. Sorry. 129 must be here. 129 must be here because 129 mod 4 is equal to 1, not 3. So where it is 63 mod 4 will be equal to 3. 8 mod 4 is equal to 0. But 8, I don't need to replace anything because 8 is a hit. 48 mod 4 is equal to 0. So LRU replacement is used. So 0 will be replaced by 48 and 32 mod 4 is equal to 0. So 32 is going to replace 4. Okay. And 73 mod 4 is equal to 1. So 73 will be placed here. And 92 mod 4 is equal to 0. So 92 is going to replace what? 92 cannot replace 8 because in the LRU 216 will be replaced because 8 has been used most recently. Okay, and 216 hasn't been used very recently at all. When you compare the 8 and 216, 8 has been used recently, so 8 cannot be replaced. 216 must be replaced by 92. Okay, so 92 is going to replace 260. I hope you got my point. After which 155. 155 mod 4 is equal to 1. 155 is going to replace 255. Got me? So which one is not present? 216 won't be present right after we access all the blocks and LRU replacement policy has been used. Okay, which is 3 there? Yes, 3 is there. Is 8 there? Yes, 8 is there. Is 129 is there? Yes, 129 also is there. Okay, here. And 216. Do we have 216? No, 216 is not present. I hope you got my point. 216 won't be present here. Can I go to the next question? Yeah, 129. Yeah. Sagar, you corrected me. Good. An 8 KB direct map write back cache is organized as multiple blocks, each of 32 bytes. The processor generates 32-bit addresses. The cache controller maintains stack information for each cache block comprising of the following: 1 valid bit, 1 modified bit, as many bits as the minimum needed to identify the memory block mapped in the cache. What is the total size of the memory needed at the cache controller to store metadata for the cache? Here, 8 is the trap where we will get locked at the 8. If you go on replacing the 8, see, you will come in this direction. 0 followed by 4. Obviously, your tendency is to replace 8. If you miss that point, 8 you are going to replace. You exactly are going to fall in the trap that has been set for you. So, if you are not wise enough, you are going to choose 8. Okay, 8 is a trap set for you. 8 KB direct map write back cache. So, I read this. Now we are asked about cache directory. What is the cache directory size? Okay, let me tell you about the cache directory size. In the entire computer system, let me tell you, I told you that the measurement of any memory is in terms of bytes. When you go to the main memory, you are going to talk the size of the main memory in terms of bytes. Even if you go to the cache memory, you will talk about in terms of bytes. The cache memory or main memory or any memory that you implement, memory will be organized in terms of bytes. If you want to organize a bit, that bit must be a part of a byte, but not in the cache directory. In the cache directory, in only the cache directory, bit is independent. Every bit is independent. Only the cache directory in any computer system, no matter which processor you are using, the cache directory size will be mentioned in terms of bits only. So we need to calculate bits only. What is the cache directory? Cache directory is total cache tag directory. Okay, cache tag directory is total number of tag bits in cache. How to calculate? For every block we do have a tag, right? So tag directory will be calculated as number of blocks into one tag size. Okay. Sometimes we will have some additional digits. that additional digit should also be added to the tag. So this will be the important point that you need to know. Only cache tag directory will be maintained bitwise, not the bytewise. You will measure the total tag directory size in terms of bits, not bytes. Okay. Now let us calculate what is the total tag directory here. Tag directory size 8 KB direct manner. First of all, we need to find out what is the total number of blocks. Cache size is equal to 8 KB. 8 KB requires 13 bits. Okay. And then main memory generates 32 bits. Just a minute. Total 32 bits. In the 32 bits, 13 bits for index. What is index? Index is as many number of bits as required to represent the cache memory. Remaining 32 minus 13 is equal to 19. The tag bits are equal to 19. Am I clear? So in 13, what is the block size? The block size is equal to, where is the block size? Block size is equal to 32 bytes. Again, this index must be subdivided into word field. What is the word field? Word field will be equal to 5 bits. 13 minus 5 is equal to 7. Am I clear? No, is it 7 or it is 8, I guess. Okay, yes. Okay, 8. So I do have a total of 2 power 8 blocks. Number of blocks are equal to 2 power 8. Tag size is equal to 19. So simply if you can have a look at the tag, every tag information also includes these two digits, one valid digit, one modified bit. So that makes total tags as 19 plus 2, which is equal to 21. So the tag directory as it is equal to number of blocks into the tag size, that is equal to 2 power 8. 2 power 8 is 256 into 21. What is the value of, what is 256 into 21? Tag bits or tag size? Tag size is, the way you use your English, I don't know. Tag size is 11 bits. Tag bits are equal to 11 bits. Okay, one tag size is equal to 11 bits. Okay, what is the option? Option is equal to 5376. Okay, shall we go to the next question? Shall I go to the next question? Yeah. The size of the data count register of a DMA controller is 16 bits. The processor needs to transfer a file of 29,154 kilobytes from the disk to main memory. The main memory is byte addressable. The minimum number of times the DMA controller needs to get the control of the system bus from the processor to transfer the file from the disk to main memory. Any ideas? How to solve this? Can you tell me what is the answer? What is the option for this? Did you understand the question? Or you want me to explain? Should I solve this? Are I say participate or what? Explain. Yeah, I will explain. This is a simple thing. The thing is, what is the DMA? DMA stands for direct memory access, right? So in direct memory access, as we do not have any intervention of the CPU, the data can directly be transferred from memory to the IO devices. For this, I will take a small background. I need to explain you a small background in order to explain you this. Understand carefully. Okay, CPU is the boss of the bus system. CPU holds the bus system, but there has to be several transfers. The data is originated at the main memory, and data will be supplied and received to and from IO devices. Okay, but bus system is controlled by the CPU. Okay, so every time when the CPU has to involve in this transfer, it will take a lot of time. CPU's clock cycles will get wasted. So in order to save the CPU time, we will take an approach of DMA. In DMA, we will request the CPU the DMA controller will request the CPU, Mr. CPU, please release the bus system. If you release the bus system, we'll be able to make the transfer directly so that your important time will get saved. So what CPU does is it will leave the bus system. At that time, there will be a direct channel enabled in between IO device and the main memory, so that the IO device and the main memory can directly participate in the transfer without the intervention of the CPU. But there is a threshold. Okay, the threshold is in the DMA controller. There is something called word count register. Okay, what is this, sir? This is a word count register or data count register. So initially, when the DMA making a request to the CPU, it will only be able to make a transfer. Let us say I want to transfer 1 GB of the file from IO device to the main memory, but I can't transfer at a stretch. Although CPU release the bus system, there is a practical limitation on the total amount of the data that can be transferred at a stretch. DMA will have a word count register. This word count register is equal to 16 bits. Initially, all the bits will be filled up. Okay. During every word transfer, this word count register will get decremented. Okay. So, right after word count register becomes 0, DMA needs to make a request to the CPU again to release the bus system. Okay. Once after the word count register becomes 0, again the bus system will be regained by the CPU. So DMA has to request CPU for one more time, for one more time, for one more time. So for how many times DMA controller should request the CPU? This is the question. Got me? Absolutely. What will be the option for this? What will be the option for this? 29K, 29,154, 20 KB. Okay. But I just have 64 KB. Okay, KB can get cancelled, and 64 divided by 154 is equal to 455 point something. So DMA should need to make a request to the CPU for 456 times, so that in order to accomplish this total transfer, which is of 154 kilobytes, DMA need to make a request to the CPU for 456 times in order to make a total transfer. Got my point completely? Option is 456. At a time, max DMA can make a transfer is limited by the data count register. 2 power 16 words can be transferred at a time. Did you get it or not? Yes or no? Yeah, 64 KB. 64 KB can be transferred at a time. So, this is the answer. Can you go to the next question? The associativity of the processor cache doubled while keeping the capacity and block size is unchanged. Which one of the following is guaranteed not to be affected? Associativity is, it can be two-way associative mapping or four-way associative mapping or a direct mapping. If the associativity gets doubled, tag size will get increased. Yes or no? Simply let us take a counter example. In a system which has a 32-bit address, I do have 5 bits for word field and 10 bits for block field or a line field, whatever you call, and remaining 17 bits for tag field. Okay, so here the thing is, if the associativity gets doubled, what will happen? This is a direct mapping. If direct mapping is updated to set associative, two-way set associative, what will get affected? Block field will be equal to block field minus 1, tag field will be equal to tag plus 1. If it is four-way, block is equal to block minus 2, tag is equal to tag plus 2. I hope you got my point. Did you understand? If the associativity gets affected, number of tag bits will get affected. If the tag bits will get affected, what are the following things will not get affected? Obviously, the tag comparator will be increased. The size of the tag comparator. Earlier, I require a 17-bit comparator. Now, I require an 18-bit comparator because from the direct mapping, I updated my cache to set associative mapping cache. So, comparator size is increased. So, it will get affected. Set index decoder. Mind you, when you access cache memory will not be random access. Cache memory will be decoder access. If you want to locate a specific block, we are going to use a decoder. within the block, we're going to follow the random access mechanism to locate a specific word. So cache will be accessed in two scenarios. In order to locate the block, we use the decoder. Within the block, we use random access. Did you get it? So in order to locate the block, I do require a decoder. So size of the decoder will get affected. Obviously, what is the here the 10 bits which will give you the block number. So if the associativity gets affected, earlier I should use 2 power 10 the size of a decoder. Now the size of the decoder will get reduced to 2 power 9, right? Yes or no? 9 into 2 power 9 decoder is actually required. Yeah, main memory minus cache plus log is associativity. Get very good. But here in the when it comes to set associative, of course, set index decoder will get affected. Way selection multiplexer will also get affected. Yeah, in a two-way set associative mapping, we use 2 into 1 multiplexer. In a four-way set associative mapping, we use 4 into 1 multiplexer, right? Of course, this will get affected. Option A, B, C will get affected, but not the databus. Bus system, databus is what? Databus is going to carry the data. Here we're just talking about the address part. So the databus will not get affected. Am I clear? Databus will not get affected. And the next thing is next question. Assume that in a certain processor, read request take 50 nanoseconds on a cache miss and a 5 nanoseconds on a cache hit. Suppose while running a program, it was observed that 80% of the processor read request result in a cache hit. The average read access time in a nanosecond is the simplest question. 14 is the answer. Am I right? Am I right? 14. Yes or no? Should I explain? Fine. I will explain this. What is the average memory access time? Average memory access time is equal to H1 T1 plus 1 minus H1 into T1 plus T2. What is H1? 80.8. Sorry, this is 0.8. T1 is 5 plus 1 minus H1 is 0.2. T1 plus T2, that is T1 plus T2 is 50, right? So this is 0.4 plus this is 10. It will be equal to, sorry, this is 5, this is not 0.4, this is 4 itself. 10 plus 4 is equal to 14. Yes or no? Got my point? Or you want me to explain it precisely? This simultaneous hierarchy, see, we are not provided with simultaneous hierarchy, but we can assume that it's hierarchical. When the information is not provided, we need to apply only this rule, hierarchical rule, H1 T1 plus 1 minus H1 into T1 plus T2. Did you get it or not? What 15? How you can get? Because see, understand carefully here. A read request take 15 nanoseconds on a cache miss. This total thing will give you T1 plus T2. Here you may try to add 50 plus 5. It is not 55. It is just 50 nanoseconds. I hope you got my point. That is, T1 plus T2 has both the time which has been spent at the cache memory, also the time which we are going to consume, which it is going to get consumed at the main memory. T1 plus T2, if you can read the question carefully, T1 plus T2 itself, it is 50 nanoseconds. Got me? The sentence is properly framed. There is no ambiguity in the sentence. He did not give you, it's a main memory access time. It's the total access time when there is a miss in cache memory. So what is the total access time? The total access time includes the time which we have wasted in the cache memory. Also includes the time which we are going to spend at the main memory. Got me? Okay. So it is 14, it is not 15. Any doubts, Sagar? If we are done, we will go to the pipelining questions. Sagar, are we done with this? Can we go to the pipelining questions? Okay, fine. The stage delays in a 4-stage pipeline 800, 500, 400 and 300 picoseconds. The first stage is replaced with a functionally equivalent design involving 2 stages with respective delays of 600 and 350 picoseconds. What is the throughput increase of this pipeline? Sagar, understand what, just enhance your doubt. So I'll come back to this question and I'll explain. Okay, just I want you to compose your doubt and post it, so that I will because we're running out of the time. This is simple. T1 plus T2 includes the term 50 has cache access time and also main memory access time. Okay, next thing is 800, 500, 400 and 300 picoseconds. I do have 4 stages. Okay, the first one is 800, second one is 500, third one is 400, and the fourth one is 300. Okay, here TP, what is TP? One segment a time, okay, is 800. The pipeline time is equal to 800 picoseconds. That is, for every 800 picoseconds, we will have an output of the instruction. Now, this has been updated to the next level pipeline. In the next level pipeline, this 800, the maximum, the time consuming, the segment is going to get divided into 2 different segments. Okay, in order to increase the throughput. Okay, TP is max segment delay, right? So this has been divided into 600 plus 350 and 500, 400 and 300. Now the pipeline time, which is TP, earlier TP in the first pipeline TP was 800. In the second pipeline TP is 600. Okay, the difference is 200. This 200 in 600 is 33%. The increase is 33%. 33.33 is the correct option. Okay, 33.33 is the correct option. So you people got the right option. So next, go to the 14th question. Suppose the functional f and g can be computed in 5 and 3 nanoseconds by functional units uf and ug respectively. Given 2 instances of uf and 2 instances of ug, it is required to implement a computation f of g of xi for one is less than or equal to I is less than or equal to 10. Ignoring all the other delays, what is the minimum time required to complete this computation is what? Okay, let us understand this question. See, this question can be solved in multiple ways. I can give you 4 and 5 ways to solve this question, but I'll explain the simplest way to solve this question. Okay, let us understand this. What is total number of instructions? Number of instructions are 10. I don't need to explain you this. Number of instructions are equal to 10. Okay, and here there are 2 functional units. One is G and one more is F. Okay, every instruction should go through G followed by F. Okay, followed by F or F followed by G, whatever you take. G will take how many clock cycles? F will take 5 clock cycles and G will take 3 clock cycles. So in order to finish one instruction, I do require 8 clock cycles. Yes or no? Clock cycles are nanoseconds. Yes, nanoseconds. So the total number of instructions are equal to 10. 10 instructions will take 8, but no, sorry, I can't calculate for 10 instruction. For the first instruction, it will take 8 clock cycles. The rest of the instruction will be equal to only TP clock cycles. What is TP? TP is max segment delay, that is 5 clock cycles. So that is 5. First instruction will take 8 clock cycles. Hold on, this is not a correct answer. This is not a proper answer. I will refine this. Initially, just understand without getting into any other details. 10 must be divided into first instruction plus 9 instructions. First instruction will take 8 clock cycles. Remaining 9 will take TP clock cycles. So 9 into 5 is equal to 45, which is equal to 53. If there is no additional information provided, that we need to understand that this will take, the total 9 instructions will take 53 clock cycles at 53 nanoseconds, whatever you call. But here there is a catch in the question. Provided there is a replica of a G, there is a replica of a F. That is, there are 2 separate functional units of G and F. in addition to this instance G and F, there is one more instance running in parallel. That means that G and F have been replicated. There are two. This is G1, F1. This is G2, F2, which works in parallel, which functions in parallel to these functional units. So here we need to just calculate only for the 5 instructions, right? First instruction followed by the remaining instruction. When the number of instructions are less, you don't apply k plus n minus 1 formula. You need to divide first instruction plus remaining instructions. So the first instruction will consume as many clock cycles as is possible as it required to cover all the segments. Rest of the instructions will only take TP clock cycles. What is TP? Max segment delay. So 5 is equal to 1 into 8 plus 4 into 5, which is equal to 28. 28 is the correct option. Got me? Did you understand this or not? Or you want me to explain it again? Sagar, Arnab, Anu, did you get this or not? Can I go to the next question? Okay, fine. I will go to the next question. If you have any doubts, you just ask me. I can explain you as many times as you want. But when I go to the next question, coming back is very, very hard. Yeah. Consider the 3 GHz processor with a 3-stage pipeline and a stage latencies V1, V2, and V3 such that V1 is equal to 3 V2 by 4 is equal to 2 V3. If the longest pipeline stage is split into 2 pipeline stages of equal latency, the new latency is dash gigahertz, ignoring delays in the pipeline registers. Here, it's a simple question. Within no time, we'll be able to solve this question. Stay focused and understand carefully. There are 3 segments. Segment 1, segment 2, and segment 3. But these segments are not provided with their direct latencies. Rather, a relationship has been given. V1 is equal to 3 by 4 of V2, which is equal to 2 of V3. Actually, in the actual question, it was given as tau, but fine, he replaced tau with a V. Fine. Now, if you can actually take 3 as common, what we will get? This S1 will become 6x. This S2 will become 8x. Even if you take LCM, you will get the same thing. This S3 will become 3x. Okay. The latency of S1 is equal to 6x. If you actually can look at this, S1 has 3/4 latency of S2 and double the latency of S3. So 6x, 8x and 3x. These are the latency. Which has a maximum latency? S2 has a maximum latency. S2 has 8x. Now we can clearly relate as T is equal to 1 by F or F is equal to 1 by T. What is this? The thing is 1 by 8x is equal to 3 GHz. Okay, what is the frequency of this pipeline? The frequency of this pipeline is 3 GHz. Okay, so as 1 by 8x is equal to 3 GHz, already we got this. Okay, 1 by 8x is equal to 3 GHz. Now what is given? In order to have a better latency and in order to have a better pipeline, what a designer has done is he divided the maximum latency into 3 equal latency stages. So in the pipeline 2, I will say PL2, S1 will remain the same, 6x, and as S2 having the maximum latency, it will be divided into 2 equal latencies, S2 and S3, okay, with 4x and 4x. And finally, this is S4, it will become S4 right now. S4 will be is of 3x. Earlier, I do have 3 segments with a maximum segment delay of 8x. In the updated pipeline, the maximum delayed segment has been divided into 2 separate segments which have equal latencies, which carries 4x latency. Okay. Now what is TP? TP is the maximum segment delay. Here maximum segment delay is 6x. Now here we need to find out the frequency. If 1 by 8x is equal to 3 gigahertz, what is 1 by 6x? So if you cross multiply, you are going to get 4 gigahertz. Yes or no? Got my points? Did you understand? Ignoring all the delays in the pipelines register, what is the new frequency? You want me to explain it again? I hope you got my point. Yeah. Anu, did you understand this? Yeah. A CPU has a 5-stage pipeline, runs at a 1 gigahertz frequency. Instruction which happens in the first stage of the pipeline, a conditional branch instruction computes the target address and evaluates the condition in the third stage of the pipeline. The processor stops fetching the new instruction following a conditional branch up till the branch outcome is known. The program executes 10 power 9 instructions. This is not 109. It is 10 power 9 instructions, out of which 20% are conditional branches. If each instruction takes 1 cycle to complete on an average, the total execution time of this program is simple. Here we need to apply a simple formula, that is pipeline time with the latencies. Pipeline time with the latency will be given as 1 plus R into S into TP. Okay, what is R? R is rate of instructions incurs stalls. Okay, S is stall cycles. How to compute the stall cycles? Stall cycles will be calculated as, S will be calculated as K minus 1. Okay, in the following sessions, I will give you a better emphasis on stall cycles, how to calculate a stall cycles. Stall cycles can be simply be calculated as K minus 1 or actual entry minus supposed entry. That is also one other way to calculate stall cycles, but I am not getting into calculating the stall cycles right here. K minus 1. What is the K minus 1 here? K minus 1 will become 3 minus 1 because in the third stage, it will be halted, where the process will start fetching new instruction in the following conditional branch until the branch outcome is known. Okay, a program, hold on. Here it is given third instruction, first stage, conditional branch instruction, computes target evaluation, the third stage, yes. So when an instruction enters into the third stage and it is found that it is a conditional branch instruction, the fetch will get stopped. So in which stage it's been stopped? K now becomes 3. So the stall cycles are equal to 2. Okay, now pipeline time with the stall cycles is equal to 1. 1 is the total number of clock cycles that are, on an average will be consumed by all the instructions as a whole, which is 1. That also given in the question, but we don't need to consider that. On an average in any pipeline, all the instructions on an average will take 1, but some instruction will take some more clock cycles. So 1 plus, what is the rate of instructions that are going to take additional clock cycles? The rate of instruction that are going to take additional clock cycles is equal to 0.2. 0.2 into what is S? S is the stall cycles, that is equal to 2. Okay. Now it will be equal to 1 plus 2 into 0.2 is 1.4. TP is anyhow, it's a nanosecond. It is negligible. TP is 1 because the 1 gigahertz processor. It is 1.4 nanosecond for one instruction. Okay. The program executed 10 power 9 instructions. So in order to execute a total program time is equal to 1.4 into 10 power 9, which is equal to 1.4 seconds. 1.4 seconds is the correct option for this. I hope I made it myself clear. With this, we have come to an end of this session. I hope you followed this session very carefully. You just watch this session as many times as possible to get a complete grip on these topics, and you solve as many questions as possible before you give the BARC HAL 2022, so that you will be able to give the exam with the utmost confidence, and I hope and I'm sure that you are going to crack this exam without any hassle. So that is it from my side. So signing off. So subscribe and click on the bell icon to the BYJU'S Exam Prep. Anil Prasad Sir here, and good night.